Hello everyone, welcome to Modeling Methods in Mechanical Engineering, and today will be our first formal lecture introducing new material. And what we're going to talk about today is the concept of fields and field theory. And in order to develop that particular concept, we're going to do so through some mathematical abstracts, and because this is an engineering class, we're also going to go straight to different applications of this concept. So this is modeling methods in ME. And let's talk about field theory. Now, a field is something that might seem very obvious to you, very mundane, but it was a very abstract concept only 150 years ago or so, or perhaps a little bit more than that. Because the concept of the idea that something actually abstract suffuses the entirety of space and it influences whatever is in it wasn't very common, and as I mentioned, it was a very abstract concept when it first came out. And the way to think about this in terms of historical references, imagine in the 17th century when Newton actually came up with the law of gravitation and his Principia Mathematica, his very famous textbook or book in which he explained all his laws of motion and gravitation and so on and so forth. He explains the gravitational effect as a force that is induced because of the mass of two objects. And he didn't actually reveal or actually try to explain where the origin of these forces was. So it's just two forces are exerted. These are attractive forces because of the effect of a mass. And these forces obviously are vector quantities because they have a direction, they have a magnitude, and they have a direction. So it wasn't until about 100 years after Newton actually published this in the late 1600s, until a French mathematician and astronomer called Laplace, this was in the late 1700s, so 100 years after Newton, actually came up with the concept of a potential field. And he didn't name it field at the time. He just called it a potential, a gravitational potential. And he said that, well, the entirety of space was actually filled with some quantity called a gravitational potential. And this potential was a scalar quantity. It didn't have direction. It wasn't a vector. It was just a quantity, like what we call right now, we would call the temperature field, for example, of this room. We know that there's a temperature field because at every point in space there's slightly different temperatures there, so there's a scalar function of temperature. But we also have vector fields, like for example the electrical field or the magnetic field, and we also have tensor fields and much more complicated things. We'll have a chance to talk about this throughout the discussions in this class. But think about this very radical concept that took 100 years to develop. Some historians attribute it to other people other than Laplace. They said that Laplace borrowed the concept from Lagrange and so on and so forth. But the point is that this wasn't a norm. It wasn't something obvious, that there was a field that permeated the entirety of space, and then you take that scalar field and took something called the gradient of that field, which is a spatial derivative over all possible directions, and then ended up with a vector quantity that is in fact the gravitational force. It has the magnitude and the direction of the gravitational force. So the equations that Laplace ended up with are no different than the equations that Newton came up with, but explaining it through the point of view of a field actually facilitated certain things, as for example the stability of the solar system, explaining certain things that were not possible to be explained with just simply calling the gravitational force a force. So this is the concept, and this is where it comes from. But nowadays we understand this concept a lot more commonly. We are exposed to it, and we understand the concept of a field much more neatly. So from the mathematical point of view, let's start by consider a function of two variables. So let's start with the concept of a multivariable function. So we call it z, which is a function of x and y. And we can explain this geometrically as a 3D surface. Right? And if we try to plot this, this is what we'll find. So, and the xyz plane, or Cartesian coordinates. So this is xy, so for every value of xy there'll be a value of z, and this will produce something like a 3D surface. So let's plot this. Let's say that this is a surface that is sort of dictated by these equations, right? And now if we take this one more step further, and let's say now we're going to look for a constant value c here of the z-axis, right? And then draw a plane let's make sure that this is perpendicular, parallel lines. And so okay, so the plane z equals c, which by the way goes on infinitely. It doesn't stop at this particular rectangle. It's just this is I'm trying to exemplify what the concept that I'm trying to make here. There's an intersection of these 3D surface with that plane, and let's say that that intersection makes up a curve sort of like this, and we call these the level curve. Okay, so the level curve of that particular 3D surface is its intersection with a plane z equal constant. So therefore, let me continue with the black ink here. Therefore, z equals a constant, which is equal to some f of x, y, defines the, or better yet, a level curve. So, as a specific example, let's say that we have the function z equals x squared minus y squared, and that if you remember your calculus 3, this is a hyperbolic paraboloid. And a hyperbolic paraboloid, I already put myself in trouble here because I don't have enough space on this page, but I'll try to fit it. This is a hyperbolic paraboloid. This is again the Cartesian system, or the Cartesian plane. And so this particular function defines a bunch of parabolas that are sort of running parallel to the xy plane. And they are connected like that. Okay, well, you get my point here. So this is a hyperbolic, so this a saddle essentially is defined by these particular functions. Now if you were to pick a constant value of z and draw a plane through that constant value, and then look at the intersection of that constant plane with so we're going to let z be equals to a constant, which is equal to x squared minus y squared. So that would be, if I do it geometrically, it would be equivalent to the figure we have above, which is drawing a plane parallel to the xy plane. And if we look at that plane from the top with its intersections, this is what's going to happen. So this will be the xy plane as seen from above, and depending on where I put that, and I'm going to use red now to define these level curves, depending on where I draw that plane, z equals c, this is what I'm going to find. So these parabolas, and I'm going to start with these, and then this parabolas coming in here. Or essentially hyperboles. Right? So depending on where that plane is drawn, I'll see a version of these particular picture, maybe these two, these hyperbole, or these hyperbole, or in fact the two straight lines. Now I mentioned before that the concept of a field is, of a scalar field, is nothing without the concept of a gradient, and so now we're going to define a gradient function. We mentioned that in the case of gravitational potential, which is a gravitational field, we have a scalar function that permeates throughout space, and then if we take the gradient of that function, somehow we'll derive the gravitational forces, the magnitude and direction of those forces. So the gradient function has to be such that turns a scalar into a vector. Okay, so let's see how we do this. So let's draw the Cartesian coordinate system again, x, y, and z. And let's draw this these vectors that run. Maybe I should use red in this case. Makes a little bit more sense. A little bit more contrast. So these vectors that run parallel to each of the axes. So this is the x. Call this one EY. And I'm going to call this one EZ. And by the way, these vectors are right on top of the axis. Okay, the fact that I have a little offset is just for illustration purposes. These are called the unit normal vectors. So EX, EY, EZ are called the unit normal vectors in the x, y, z directions respectively. Okay, well, we call them normal, but in fact they're actually tangential. They're the opposite of normal. They're tangential to their own axis, but they're normal to the opposite plane. So the x-axis is normal to the xy, to the yz plane, and therefore this vector here is normal to the yz plane. What do we call them? Unit, because they're unit in length. Okay, regardless of the physical units that we're using or the engineering units that we're using, whether this represent velocity, position, force, momentum, energy, whatever is it that they're representing, they're unit in length. Their size is 1. Okay, you might have seen these vectors in other classes. Some people call them I, J, K. Okay, there's the same thing. There are some people in the electrical engineering literature, they like to use this hat thing to enunciate that these are vectors in unit in length. So they're all different poems of the same thing. All right. So the gradient is denoted by the Greek symbol, not letter. This is not a letter. This is just a Greek symbol, Nabla. And it's an operator that takes the derivative of a function in each of its directions and multiplies them times the unit normal vector in that particular direction. Okay? By itself, this doesn't mean anything. It's an operator, so it has to be operating over something. It has to be Nabla of something. Okay? So this right here is known as the del operator, where this upside down triangle is the Greek symbol Nabla. Nabla. Okay, so the way it works is very simple. This is an operator. By itself, I mean, as I mentioned, it doesn't mean anything. It looks like a vector. It has 3 components, yes, but it is taking the derivative of something. So some people would like to write this operator as just basically this with some parentheses in it to denote that you're taking the derivative of something. So, for example, given a function f of x, y, and z, and we're going to denote this as a scalar function. Scalar function. Okay, now we're looking at a function of 3 variables. Okay, not z is a function of x and y, but a whole function of x, y, and z. What could this be, and what could be scalar? Again, a field. For example, the temperature field. The temperature in this room. Okay, let's say that this room, we're going to frame this room in the Cartesian coordinate system. Let's say we put the origin at that corner right there, and then we say that that's z, that's x, and that's y, right? And then we define a function of temperature inside this room and say, well, the temperature here maybe is 22 Celsius. But as we get closer to the roof, or I'm sorry, the ceiling, where there's a lamp, the temperature might be 23.5 because it's a little hotter. And also heat has a tendency to rise, or hot air has a tendency to rise, that is, not heat. And therefore, you'll have a distribution of temperature. We call that distribution, the function of x, y, and z. We call it a field, a temperature field. So let's just make it general and call it f, right? So we can calculate the gradient of f, which is illustrated as Nabla f, which is read as del f. Okay, so we have 3 ways of saying the same thing. Grad f is equal Nabla f, which is also read as del f, is essentially the partial derivative of f with respect to x. And that is multiplied as a uninormal vector in the x direction. So now we have an x component to a resulting vector, df dy in the y direction, and df dz in the z direction. Okay. And I'm sure you've seen this before. And basically what it means is that we are calculating the spatial partial derivatives of the multidimensional function f in all directions, resulting in a vector field. So these actually results into a separate function, and that separate function is a vector field, unlike this f, which is a scalar field. So this new function that you end up with has a direction, has magnitude and direction, but it's still a function. So there you have it. So let's look at an example of these. And example. Let's say that, again, we have a function z of f of x and y. Again, we're back to a function of 2 variables. And this is a scalar function defined by these polynomial. Okay, 5y minus x cubed y squared. What does that mean? Nothing. It's just a mathematical construct. But it could potentially mean that that is the temperature field is a scalar. Temperature is a scalar. Temperature doesn't have vector components. Temperature is a scalar. And because it's in 2 dimensions, this could signify potentially, for example, the temperature field on the surface of this table. Okay, the surface of this table is 2-dimensional, and let's say that this is the x direction and that's the y direction. And depending on the position on this table, we can say the temperature here is such, the temperature here is such, and such and such. And it's all basically defined by this function 5y minus x cubed y squared, whatever that means. Okay, then we can calculate the gradient of f, which is also denoted as Nabla f, or read as del f, is df dx in the x direction plus df dy in the y direction. So grad f is equal to the partial derivative of this function 5y minus x cubed y squared in the x direction, multiplying the uninormal vector in the x direction, plus the partial derivative with respect to y of the same function. So you take the same scalar field and calculate its partial derivative with respect to y now. And so you end up with grad f, which is the same thing as Nabla f, is simply the partial derivative of these with respect to x. Remember, when you take a partial derivative, everything that is not an x, it's assumed to be a constant. So in this case, in this particular term, both 5 and y are constants, so the derivative of that is 0. And in this particular case, y squared is a constant, so what you end up with is minus 3x squared y squared in the x direction. Plus these, when you take the derivative of these with respect to y, you end up with 5 minus the derivative of these with respect to y will be 2x cubed y in the y direction. So notice how we magically took a scalar function like this. Scalar, it doesn't have direction, it's just at every point in space, x and y. You evaluate this at every point of x and y, you just get a number. Okay, you don't get a vector. We took that and magically turned it into a vector field. Another function that is somehow associated with this one, but it has an independent function in x and an independent function in y. And when you evaluate it at any point in space, x and y, you get a vector, a number here, and you get a number here. And that vector has a direction and it has a magnitude, as you can see. And that is the concept behind field and its gradient, a potential field or scalar field and its gradient. Okay, this could potentially be the gravitational potential field of a particular influence, and then this could be the force that results of that potential field. All right, now to a more common application to us mechanical engineers. This is again very mathematical, what we just did, but for us, let's look at an application. And one that we are going to be visiting very often, which is the application of heat conduction. So the temperature field of a 2D plate or surface, like I said, the surface of this table, is given by these potential field or scalar function t of x and y. Okay, so again, the surface of this table is a 2D plate, right? And any point of x and y, if we define x in this direction and y in that direction, then at any point x and y, we can obtain a temperature, different temperature on this field. So then this French mathematician called Fourier, same guy as the Fourier transform and the Fourier law and so on and so forth, Fourier law of heat conduction states that the heat flux is equal to a constant of proportionality, which is called K, times the gradient of x and y. So taking a scalar field like the temperature, taking its gradient and multiplying times a constant results in a vector field, and that vector field is sort of the energy that is carried by this temperature in the form of conduction, right? This is the law of heat conduction. So where Q is the heat flux vector, the heat flux vector. Okay, by the way, anything in engineering that we call a flux, or in engineering science that we call a flux, is because it's in units, or this particular heat is in units of energy. Flux means per unit area per unit time, so this is energy per unit area per unit time. So this is sort of like the energy density, not density because it's not per unit volume, but it's the energy per unit time. It's just the rate of energy or the power per unit area, so that going through a particular surface or infinitesimal surface. And K is what we call the thermal conductivity, is the thermal conductivity. And we call this just a constant of proportionality between the gradient of T and K and Q and the actual energy that is carried, because that actual energy depends on the material in which it propagates. So materials are in which it's easier to conduct heat have a high thermal conductivity, like for example metals, silver, copper. So it's usually the opposite of electrical resistivity. So a material with high electrical resistivity, an insulator usually would have a low thermal conductivity and vice versa. Okay, now if we want to put units to this, because we're engineers and it's always very advantageous and beneficial to use units so we make sure we don't make a mistake when solving a problem. Let's say that the temperature field is given in Kelvin or degrees Celsius, Kelvin. Okay, the thermal conductivity is in watts, meters, Kelvin, and the heat flux, even though it's a vector, each component of that vector has units watts over meter square. Because it's a flux, is energy or heat, and the flux means per unit area per unit time. That's what flux means. So you take the heat, which is units of energy, right? Per unit area, there's a meter square, and per unit time, this energy divided by time gives you power, which is watts. Okay? So we have then that the heat flux vector in a two-dimensional field will be minus k times dt dx in the x direction plus dt dy, that's the gradient of t, in the y direction. And by the way, if the temperature field was defined in 3D, like in this room, we can calculate the vector, the heat flux vector, the same exact way. We just add another dimension to it. No big deal. Now the last thing to sort of comment on or figure out here on this and these expressions is why there's a minus sign in the middle. Well, if you think about this carefully, you'll notice that it would be the only way to ensure that the energy arrow goes from high temperatures to low temperature, which is nothing but a convention. Okay, so if we want the energy to flow from high temperature regions to low temperature regions within a solid, for example, or from a hot body to a cold body, the only way to ensure that through this definition of a gradient is by sticking a minus sign in front of it. That's the only reason that minus signs exist there. It's just because of this universal convention that says that heat will flow from hot to cold. Okay, which is an abstract definition. We could have done it 200 years ago in the opposite direction, and we wouldn't have seen a negative sign there. Okay, so that's the reason why there's a negative number there. All right, so let's look at the concept of directional derivative. We know that the gradient will produce a vector field given a scalar field or a potential. We'll take the gradient and then produce a corresponding vector field, and then we can also use that gradient to calculate something called the directional derivative. And the directional derivative is nothing but the derivative in a specific direction. That's it. So the directional derivative du, that's what we call the directional derivative of a function f, is equal to the gradient of f dotted into the unit directional vector u. Okay, that's what we call it du, directional derivative over the direction of the unit vector u of the function f. Okay, it's the gradient of f dotted into u. This dot right here is called the dot product or the scalar product, and it's called the dot product or the scalar product because when you take the product of two vectors in this form, you end up with a scalar. So if you take this vector, we know that the gradient of a function is a vector, and we know that this unit normal vector or unit vector is a vector. When we take the dot product of the two, we end up with a scalar. So again, this is the dot or scalar product, and u is any unit, it has to be unit, and magnitude. So the size of the vector in which we want to take the direction, or over which we want to take the direction, has to be unit in length for it not to influence the resulting value of the directional derivative in a direction of interest. So if we know the direction in which we want to take the directional derivative, we have to define that direction by a vector u, and that vector has to have magnitude 1. It has to be unit. Okay. Now, what if we're given a direction, or we can figure out a direction with a vector that is not unit? Well, we can construct a unit vector from a non-unit vector and maintain its direction. So therefore, if the direction is given, if the direction is given by a non-unit vector, so we're told that, for example, the direction goes from here to that corner, and then we can calculate that we can subtract the coordinates of the 2 points and end up with a vector that is not necessarily unit in size. We can always figure out the unit version of that vector by taking that vector, big U, and dividing it by its magnitude. Okay, so that's how it works. Very simple. So for example, let's say that we're given a vector cosine of theta in the x direction plus sine of theta in the y direction. And notice that I am writing that vector as a unit, and it's a lowercase u, so it's unit in size. And we know for a fact that that vector will always be unit in size, regardless of what the size of theta would be. Because if I take the square of the first one, the square of the second one, add them up, and take the square root of that, I'll get 1 because of a trigonometric identity. So let's say that this defines the directional, or the direction perpendicular to the tangential coordinate theta in the xy plane. And we know that the magnitude of u is equal to the square root of the square of each of the components of that vector. So cosine of theta square plus sine of theta square, which is a cosine square of theta, plus a sine square of theta, which is 1. Okay, so let's just expand on this. Which is the square root of 1, which is 1. Okay, so it's in fact unit in length. All right, and we can, let's just make sense of this expression that this vector defines direction perpendicular to the tangential, which is sort of contradictory because tangential and perpendicular are two opposite things. But this is the tangential. This is the tangential coordinate in the xy plane. This is theta. So we can define it at any radius. So we sort of did an implicit transformation into polar coordinates. So same thing, theta. So if we pick an angle, let's say we pick a specific angle, theta, then the unit vector will be perpendicular. It's perpendicular to the tangential direction, right here, perpendicular to the tangential direction. That's u. Okay, defined as the cosine of theta of this particular angle was 30 degrees. So the cosine of theta, square root of 3/2 in the x direction and 1/2 in the y direction, for example. So those are the two components of that vector. So if we do that, and let's say we are given now that given this field, again a scalar field f, which represents whatever physically. Right now it's just, again, mathematical expression, but it could represent the temperature on a plane, or it could represent whatever scalar field there could be in a plane. Find the directional derivative of f at point 1, 1, that's x equal 1, y equal 1, in the direction perpendicular to the tangent theta at theta equals pi over 6, which is 30 degrees. Okay, so let's plot this. X and Y, and we have some kind of field permeated all over space here, so this is field F. Okay, so it's essentially the level curves of the field F projected on the xy plane, because remember that these actually represents a 3D surface, right? F being whatever other variable, the temperature. So this is a 3D surface. But when we plot the contours of F on the xy plane, this is what we see, the level curves. And then we're asked to take 0.11, 1, and at this point in the field, we are to calculate the derivative of these fields. If we take the gradient, we'll get a vector, right? And the vector will give us the partial derivative in the x direction and the y direction. But now we want exactly what happens in the direction u, which is at an angle theta equals pi over 6. Okay, what happens? What is the derivative of the function exactly in that direction? Perhaps because that direction is something special. It basically might mean that that is the direction in which we want to build a sensor, a line sensor, and then we want to know what's happening to that function along that line and at that particular point. So we can take the gradient of f, which is the x and the x direction, plus the partial of f with respect to y and the y direction, and then the gradient of f will be the partial with respect to x. I'm doing this in multiple steps again because we're introducing this concept. Dx plus d dy of the same scalar function. Okay, and the y direction, don't forget about that, because the gradient of a scalar function turns into a vector, so never forget the vector components. So Nabla f, or del f, is essentially 4xy cubed plus 6y in the x direction plus 6x squared y squared plus 6x in the y direction. We can further simplify this by taking the 6 outside, or whatever that means, whatever you need. So you can take a common factor here. You can take 2 outside, and this will be 2x cubed, xy cubed, I'm sorry, plus 3y. You can take the whole 6 outside, whatever you want to do. But at the end of the day, we're only interested in the directional derivative, which is a scalar, and at a particular point, it would just be a number. All right? So we can either take this and multiply times the vector u, or while we're at it, we can just evaluate this derivative, or this gradient, at 0.11. So what happens if we evaluate this gradient at 0.11? We get 4 times 1 times 1 cubed plus 6 times 1, all of these in the x direction, plus 6 times 1 squared times 1 squared plus 6 times 1, brackets, in the y direction. So the gradient of this function, f, which is a scalar function, it's a vector field. So a field means that it's a function. But now evaluated at a point, all we get is just a vector. So this is a vector. This is not a directional derivative because we still have a vector, but it's a vector with just 2 numbers. So this is essentially the derivative of the gradient of this function at this particular location. It is increasing by a factor at a rate of 10 in the x direction and a rate of 12 in the y direction. Okay, so now we want to calculate the vector u. The unit normal vector is defined as cosine of theta in the x direction, because we were given a tangent direction, so we can just define the vector like this, which is the cosine of pi over 6 in the x direction plus the sine of pi over 6 in the y direction. So u is equal to square root of 3 over 2 in the x direction plus 1/2 in the y direction. So the cosine of 30 degrees and the sine of 30 degrees. Okay? And finally, so that's the vector, that is the gradient evaluated at that point. So the directional derivative of the function f evaluated at 0.11 would be the gradient of f evaluated at 0.11 dotted into u. Dot product. Don't forget the dot. It's completely different as cross product. This is dot product or scalar product. So this will be 10 in the x direction plus 12 in the y direction, dotted into a vector that is square root of 3 over 2 in the x direction plus 1/2 in the y direction. And the way the dot product works, if you remember from your calculus 3, even in physics, you take the x component of these, multiply times the x component of this, you take the y component of these and multiply times the y component of these, and if there were a z component, you do the same, and then you add them all up together. So the directional derivative of f at 0.11 along the direction u is equal to 10 times square root of 3 over 2 is 5 square root of 3, and the vector component disappears. So it's plus 12 times 1/2, which is 6. So notice this, even though you have two separate terms, they're not separated by components, it's just a scalar. So the directional derivative of a function, however many direct dimensions that function has, ends up being just a scalar. And evaluated at 0.11, that scalar just becomes a number. And the number in this case is 5 square root of 3 plus 6. And that's it. So I'm going to stop here, and this is the first lecture on field theory, and we'll continue along this subject and on the follow-up lectures. We'll discuss several things that we can do in terms of these vector operators and integral identities and so on and so forth that are defined with the same type of concepts. So thank you for your attention, and I'll see you next time.